learn PowerPoint on applications of 3D vectors. We've got quite a few notes on these, so I'm going to break this into multiple videos so we don't end up with one that's over an hour long and tricky for you to navigate. I will go faster than I would go in a classroom because you can pause and go back and rewatch things as you need. So here we go with just 2 examples for this video, and then I'll keep adding in the next. So first one we're going to look at is the distance between parallel planes. So we're looking at 2 planes that are running, parallel in space. So we've been given 2 planes. They're defined by r dot 2 negative 1 3 equals 8, and the second plane is r dot negative 4 2 negative 6, that equals 5. So the first thing we need to do is check that these planes are parallel. So obviously if they're parallel, then that must mean both of their normals are going to be parallel as well. So first thing we need to see is, can we take out a scalar multiple to identify what both of these normals would be. So negative 4, 2 and negative 6, hopefully you can see if we pull out a factor of negative 2, we end up with 2, negative 1, 3. So in fact we can see that this is a multiple of this normal, so they are going to be parallel. If I was to then rewrite this second equation so it does have the same normal, what I'm doing is taking out that factor of negative 2, and so I end up with negative 2.5. So hopefully you can see, so I've gone from negative 4 to negative 6. I know I have to divide that by negative 2 to get to negative 1, 3, and then obviously I'll have to divide the other side of the equation by negative 2 as well. Now just a little note with this, so now we've got these 2 equations. Obviously the r dot normal is identical for both sides of the equation, and what we have here is 8 and negative 2.5. So in terms of what this looks like in, out in the world, or on our axes, this would mean that these 2 planes, while running parallel, will actually be on opposite sides of the origin. And while you're not expected to have to graph this, that's an important point because it's going to help us with the next part of our question, which is finding the distance between these. So we're going to look at 2 methods for finding the distance. The first one's using scalar product, and then we're going to look at another method after that. So let's look at what we know first. So in our first plane, we know that r dot, the normal, so we'll just call that n1 for now, equals 8. So we know with our dot products from our formula, we know that r dot n1 is going to be the magnitude of r, the magnitude of n1 cos theta. And if we do a little bit of rearranging, we get 8, because obviously r dot n1 equals 8, so make sure you agree with that. So all I've done is put 8 in place of there. So we know 8 equals the magnitude of r, magnitude of n1 cos theta. So again, we can do some rearranging. And what we can do now, because we actually know the magnitude of n1, those are just that's the vector that we've been given, we want to actually look at, well, what does this magnitude of our cos theta represent? So in this quick little sketch we've got here, so we've got some plane going through space. I know it's tricky to see the 3D aspect, but we are assuming that there's a 3D aspect and there's this plane, and we're obviously just looking at the plane dead from the side, so you can't see the 3D, just to keep our graph simple for now. So we know on this plane, the r represents any point on that plane. Okay, so I've just picked any point. You could have picked any point along r. All right. We know the magnitude of r is the distance from the origin. n1 is normal to the plane, so we're looking for the perpendicular. And to make it simple, I'm drawing the normal through the origin, because obviously we can draw the normal anywhere. Any line that's perpendicular to the plane could be a line here, could be a line here, could be a line here, but we're going to go through the origin to make it simple for ourselves. So now hopefully what you can see is we have made, and I'll just put that there, obviously this is going to be a right angle. A little bit hard drawing with the mouse, but hopefully okay. So we've got a right angle. We've got our magnitude of r. The angle that we're looking at is obviously this angle here, right? And so if we were to say what is the magnitude of r cos theta, that's going to be this line here, isn't it? Just here. Because cos is the adjacent side. So we know cos theta equals adjacent over hypotenuse. So if we rearrange the cos theta equation, that's going to give us this side here. So that's what is actually being represented. So the distance the plane is to the origin is actually the magnitude of r cos theta, which we can say is 8 magnitude normal. And because we know the normal, we can find the magnitude. And you guys, I've obviously gone to the next slide, but check that you agree with my calculations. So the magnitude of our normal is going to be the square root of 14. And so we've got 2.138. So what we've calculated is that red line there. So sorry, again, drawing with a pen, with a mouse is not as easy as I hoped. So I'm doing this line here. That's what I've found. That distance there is 2.138. Now, if we were to do the same thing for our second plane, and remember we've already determined that the planes are parallel, excuse me, so that's why we know this strategy works. So we are looking again, the distance, we can do the same thing. We know that the constant was negative 2.5. They have the same normal. It doesn't matter. They have the same normal. It's the square root of 14. So now the distance is going to be negative 0.668. So again, that's referring to this plane over here. And because we had positive 8 and negative 2.5, they're on opposite sides of the origin. So now this is our 2.138, sorry. And I was hoping I could get a different colour from my pen, and I can't. But anyway, the second one, the distance here to here is what we've calculated next. That's our negative 0.688. And so the total distance between the planes is this amount here. Okay, so that's one method. Right, we're going to look at a different method now using the normals. All right, so now again, looking for the distance between the planes. So now this one doesn't use the origin, so this might suit your way of working things out a little bit better. So this time we're just going, all right, we've got two planes, we know they're parallel. We are going to look at the distance between planes. We know because the normal is 2, negative 1, 3, the distance between them must be some scalar multiple of that, doesn't it? Because we've gone perpendicular to plane 1, it's also going to be perpendicular to plane 2, so we're looking for some scalar multiple. So let's call the point on plane 1 point P. And if we work out that obviously point P has to come from the origin, we can also then say that on the plane, second plane, we've got point Q, excuse me, point Q. And so now we can start defining our OP, our OQ, and our PQ, and start working out what this scalar multiple must be to work out the distance, okay? So point P, we don't know what that is. Let's call it ABC. We also want to work out OQ, which we know is going to be OP plus PQ. So we know OP we defined as ABC. We know a PQ is some multiple of our normal. We also know that because Q is a point on plane 2, it must satisfy the plane 2 equation. Okay, so we know that. So we can take that information and say a point on Q, which is what we've worked out. We worked out this is what point Q represents. It must satisfy this equation. So what we've done is we're going to put all of this in place of our R, okay? Because R represents any point on the plane and Q is a point on the plane. From here, we just start simplifying. We've just done our dot product. We'll expand out the brackets, ready for our dot product. All right, next slide. So carrying on from previous, now again, let's see what we can actually simplify. So ABC dot to negative 1, 3 is a point on this plane, isn't it? So because we know ABC is point Q, it's a point on the first plane, so it must satisfy this equation. So that means that point, doesn't matter what it is, that point substituted in here has to equal negative 2.5. So we've replaced that with negative 2.5. Right, keep going through. So we've just done our dot product there. Simplify. Simplify. So we've worked out our scalar multiple is 21, 8. So we know that's what we're going to multiply by. That's our distance between points. So it's going to be the magnitude of 21 over 8 times that normal, which gives us the same answer that we did before. So it is a tricky question to do. Both examples have their pros and cons, so both methods, so you choose what suits you best. Okay. All right, one more example for today. All right, we've got an intercept collision situation. So we've got a satellite situated at a certain position and its velocity vector. The Enterprise, with its position vector, wants to shoot the missile. So, and that we know the missile can travel at 4 root 27. So we want to work out, if we know the magnitude of that velocity, what should be the velocity vector so that they actually hit. Okay. So let's start by looking at the satellite position. So there's our satellite position in regards to the origin. We know that the satellite's velocity going off is 8, negative 4, 2. Let's look at the Enterprise position. So obviously this is its position relative to the origin. And it's going to have some velocity. We don't know what, but we want this collision. All right, we want to make sure that it hits that satellite at whatever point that will be. All right, and we'll call that the point of collision. All right, let's start writing down what we know. So we know that the magnitude of this, so let's take it out of surd form. So we know that these three values squared added together will be the same as this magnitude squared, which is 432. Check the calculations, make sure you agree. And now what we're going to do is we're going to say, all right, we can define this point C using both S and some velocity here, and then E and some velocity here. So OC is that satellite position plus the velocity of the satellite for some value of t. We also know it's the Enterprise's position plus some velocity, and again these obviously have to be the same because we're going for collision, of x, y, z. We can make these equal one another for our I components, j components, k components. Now I tried to throw this straight into a calculator and I didn't like it, so I had to do some rearranging first. So if we rearrange for x, rearrange for y, and rearrange for Z and put that into the calculator after that. I got, and obviously making sure you're putting in this one as well. We need to put this into our calculator as well. Oh, sorry. And that should give you x, y, z, t. So that's going to be our I component, j component, and z component of our velocity vector. And the time, not that it was asking for the time, but a nice one to have, it would intersect and explode the missile, satellite, at time 1.98 seconds. Okay. All right, we'll stop there, guys, and we will add to this in the next video. Thank you.